My name is Themistoklis Tsalkatidis, and the title of my presentation is Numerical Investigation of Reinforced Concrete Beams Strengthened with Basalt Fiber Reinforced Polymer. As introductions, let's discuss about some definitions of repair and strengthening. So first of all, repair is the process of removing damaged and decayed parts and restoring the integrity of the structure or an element, whereas strengthening is the process of upgrading a structure to improve its structural performance. In this presentation and in this paper, we will use the concept of strengthening. Which are the reasons for using strengthening? First is structural deterioration and damage in a structure is to increase the capacity demand to meet modern building codes if we have like an old structure, and to correct original design flaws. The results of using strengthening are we increase the load-bearing capacity of the structure or the structural element, we enhance its durability and ductility, and overall we extend the service life of the structure, thus making the structure a sustainable project. The more common strengthening techniques that are used worldwide are, first we have the externally bonded reinforcement. As a reinforcement, we can either use a steel plate or FRP. FRP stands for Fiber Reinforced Polymer, and there are many different types of FRPs, such as carbon and basalt and glass FRPs. We could also use internally bonded reinforcement. So this is near surface mount reinforcement with use of epoxy or grout in order to embed this reinforcement. We can also use jacketing. So this is basically enlargement of the cross section of the element. External post-tensioning and shotcrete. So this is basically sprayed concrete on the outer surface of the existing element that we need to strengthen. Which is the aim of this paper? The aim of the paper is to investigate and quantify the effect of strengthening with externally bonded basalt fiber reinforced polymer, BFRP, the effect of strengthening on the structural performance of a simply supported reinforced concrete beam using numerical analysis. The analysis was conducted using Abacus software package. The beam examined, made of reinforced concrete, is a simply supported beam, 2 meters in length, and the beam has a rectangular cross section of 150 by 250 millimeters. We applied 3 different configurations of basalt fiber reinforced polymer with full and strip wrapping, and the thickness of the polymer has been equal to 0.14 millimeters. We have a control case of the beam without using BFRP, and for the numerical models, in order to verify the models, we used the experimental results from Seismic et al., which is a paper that was published in 2021. Let's now see the material properties that have been used in the models. So we have, first of all, for the concrete, modulus of elasticity equal to set to 13 gigapascal, the compressive strength set equal to 20 megapascal, Poisson's ratio 0.18, and for the concrete damage model, we use the parameters from Taraki et al. you can see the parameters in this small table. For steel, we use modulus of elasticity equal to 210 gigapascals, yield strength of 210 megapascals, and Poisson's ratio of 0.3. For the basalt fiber reinforced polymer, these are the parameters that we used for the material. And for the epoxy, we use standard contact with 0.15 friction coefficient. So this is a feature of the Abacus software package. Let's now see the three different model configurations. So for the first model, which is named FWCS90, 90 denotes the orientation of the fibers. You can see the geometry of the beam, the placement of the loads, the support placement, and with green color we can see the BFRP wrap. So in this case we have full BFRP wrap with a length of 500 megapascals. The placement of the wrap is symmetrical. In the second model, FWS90, we don't have a full wrap, we have this stripped wrap. You can see the width of the strips and the distance from of the first strip from the end of the beam. In total, we have used 10 strips. Model 3 SB90/9/0. So in this case, we have full FRP wrap, but the length of the wrap is 750 millimeters instead of 500 millimeters that was in the first model. This is now a slide with the three different BFRP wrap configurations. So for the first model, we have full BFRP wrap, and you can see that the wrap extends all over the perimeter of the cross-section of the beam. In the second case, we have these strips, again all over the perimeter of the cross-section of the beam. And in the third model, we have this U-shaped wrap. So this means that the top part of the beam, of the cross-section of the beam, is not having any BFRP wrap. For the steel reinforcement, we have used both longitudinal and reinforcement and stirrups, and you can see the configuration of the steel reinforcement as it appears in this slide. Let's now discuss about the results. First, present the results. So we have now a slide with the shear force displacement curve, the control case without BFRP, and the three models with BFRP strengthening. So with this green line, green curve, we can see the control case, which has significantly less shear force development and displacement, and the three other cases. So in the third case, we can see that we have the development of the highest displacement, whereas in the first case we have the max shear force in comparison to the other cases. For the shear capacity, let's see now this table. So we have again the control case and the three models that we have used the different configurations of BFRP. By comparison of the columns, we can see that the error in each case is very small, is 5 and less than 5%. In the second case, which is model 1, it's practically non-existent, the error percentage. And you can see also the values of the shear forces measured both in the experimental and the finite element analysis. So as you can see, the results are very close. For the vertical displacement and crack width, so these are the contour plots from the Abacus model. So on top we have the vertical displacement, and below we have the crack width. So we have used a command from Abacus. You can see here the acronym of the command and the table. So in this case, for the 3 models, we have the first column that depicts the experimental displacement at ultimate load. The second column for the numerical analysis, the displacement at ultimate load. And then we have the crack width, the experimental one, and the fourth column depicts the crack width from the numerical analysis. So the values are in millimeters. So as you can see from the crack width, the model gave very good results in all cases. For the experimental displacement, so there is some difference between the experimental and the numerical result, especially in cases of the model 1 and model 2. To sum up the conclusions of this presentation, in general, the use of externally bonded BFRP wrap improves the structural performance of a reinforced concrete beam. We have an increase of the shear capacity of the beam up to 57%. We have a decrease of the shear crack width up to 23%. And we can say that overall, these numerical models that we have presented can be used as a design tool in problems of strengthening reinforced concrete beams with basalt fiber reinforced polymer. Thank you for your attention.